Okay, welcome to lecture. We'll get started here in just a second. Again, a reminder, please type here in the chat box if for roll. And also, obviously, if you have any questions, you're welcome to ask them there throughout the time. And we're continuing on with chapter 1 where we left off. And again, the lecture notes should be up on Canvas if you need them. And you can follow along and use those if you wish. Also new up there as well, chapter 2, which is our next chapter as after we're done with this one, which we'll probably get to maybe today, maybe Wednesday. So again, those are up there as well for you to use. And again, we'll get started here in just a sec. And last time we were talking chapter 1. So we talked about atoms, we talked about molecules, elements, some basic sort of chemistry stuff as well, in addition to mixtures and different types of mixtures, homogeneous mixtures, heterogeneous mixtures. We also talked about taking measurements, and when you do take measurements, there's always some degree of uncertainty that's associated with that measurement. And remember that that's sort of where we were finishing up here. The idea is when you do take a measurement, you do want to make sure that you look at the scale on the particular piece of equipment that you're using. So if it's a ruler, if it's a graduated cylinder, whatever it may be, there should be some type of markings that are there. And again, what you really want to try to do is figure out what those smallest markings represent. So for example, if, do that there. For example, if we have the smallest markings, that is 0.1 centimeter, that means that typically you could go to one more place of the smallest marking, which means you would be able to go to 0.01 centimeters. Got one sec here. So if we again looked at something like a ruler, and each of those little markings, you know, between the big numbers was 0.1, you typically go one more place when you take that reading, and you would want to record it to the second decimal place when you do that. So here we go, getting everybody in. When we do take a measurement, the important part about when you do take that measurement, as we talked about, is you want to make sure that you always record all the certain numbers. So remember that as we were talking, no matter who takes a look at it, there always should be certain numbers that everybody should definitely agree upon. And no matter who looks at it, you know, they should definitely say, hey, it is at least this much. But then there's always going to be a digit where there is going to be some uncertainty involved with it. And again, I may look at it and go, I think it's halfway to the next mark, or somebody else may look at it and go, I think it's pretty close to that next mark or closer to the first marking. And that's really where the uncertainty in a measurement comes into. And when we do record a measurement, always all the certain numbers plus the first uncertain number. So always want to record all the certain numbers in a measurement plus the first uncertain number. And when we do that, what that means is that is essentially the significant figures. And significant figures really is that when you have a measurement, for example, and you record all those certain numbers plus the first uncertain number. Now, the uncertainty in a measurement lies in the last significant figure. So again, that's really important when you're asked, for example, like you might this week in lab, you know, which one is the uncertain digit, or where is the estimation happening? And, you know, 9 times out of 10, it will be the last digit in the number, but not 100% of the time. It is, though, the last significant figure in the number. And really where that plays into effect is it has to do with the zeros and whether or not, you know, the ending numbers are significant or not. So that brings us to, I think, where we left off. And again, here, we're going to talk about really the rules for significant figures and the guidelines here for significant figures in terms of how you properly count them. And again, those people just come in, make sure you do right here in the chat box for a roll. I appreciate it. So let us talk about how we actually figure out what is a significant figure or not when we do have, say, a measurement, a number given to us. The first rule is pretty simple. Anything that is a non-zero is a significant figure. And that's really what you want to look for when you're starting to count significant figures. You want to figure out which one is a non-zero, usually left to right, and that's where you want to start counting. We're going to actually get to your question in just a second. So I'll get to your question about the zeros there in just a second. So for example, here we will start counting here. This is our first non-zero number. And then obviously all the rest of these are non-zeros. So this guy would have 4 significant figures here. They would all be significant. So that's pretty simple. Any number that is not a zero is always going to be significant. And you do want to obviously count them. And the important part, though, is you don't want to start counting until you hit that first non-zero number going left to right on a number pretty much. Now, when we go to zeros, these are really the ones that give people the hardest time when they're trying to figure out, you know, is it a significant figure? Is it not a significant figure? And really, there's 3 different types of zeros that you come across. The first type of zero is sometimes referred to as a leading zero, and those are not significant. So you could have as many zeros as you want heading into that first non-zero number. They will not be significant. So in this particular case, we wouldn't start counting until we hit this 2. And then the 5 would also be significant. So this guy here would have 2 significant figures in this particular case. So again, you could have as many zeros as you want heading into that first non-zero. They're not going to be significant until you hit that very first non-zero number. Now, the next type of zeros are what are sometimes referred to as confined zeros. They're also sometimes referred to as being trapped zeros. And these are zeros that are between 2 non-zero numbers. And zeros that are between 2 non-zero numbers are essentially always going to be significant. So if we look at this number here, we would start counting at the 1, as the 1 is a non-zero. So that is our first significant figure. The 2 zeros that are trapped in the middle there are also going to be significant because they're trapped between 2 non-zero numbers. And then the 5 at the end will also be significant, which means that this guy would have 4 significant figures in this particular number. Now, the next type of zero is really the one that gives people super hard time. And it is, I think, the question that you were asking there. It has to do with those zeros that come at the end of a number. And the zeros at the end of a number, they may be significant or they may not be significant. And it is one thing in a number that determines whether or not those zeros at the end are significant, and that is a decimal. So if you got a decimal point anywhere in the number, it does not have to be like right next to the zero that you're looking at. It just needs to be somewhere in that number. It will be significant, all the zeros that come at the end. If there is no decimal point written in the number, then that zero is not going to be significant. So when we look at this guy here, if this was a measurement, and I could draw a straighter arrow there, we'll kind of tilt it up there. That 100 written like that, there's absolutely no decimal in that number the way it's written. So that would imply that the 1 here is the only significant figure. So this would have 1 significant figure. The other 2 would not be considered significant figures because there is no decimal point in it. Now, if we take 1.00, the 2 zeros here at the end now become significant because there is a decimal point in the number, and this would give us 3 significant figures in this particular case. So the 0 at the end, or multiple zeros at the end, will only become significant if there happens to be a decimal point in the number. So for example, if you had a number such as 0.0001003004000, why not? Take a second and count up how many significant figures you think that has, and I will tell you the answer. We'll go over the answer here in just a second. Okay, so let's take a look here and see, what we got going. I don't know either because really I just made the number up. So let's take a look and kind of see how many zeros and stuff I put in there. So if we start counting, let's drop a different color here maybe. Let's see, 10. Let's see if you're right. I have no idea. 13. I see multiple answers. So let's take a peek here and see. Well, at least nobody said like 320. That's good, right? All right, so here we go. We're going to start here left to right. And again, all these zeros here are not going to be significant because we have not hit the first significant figure yet. So starting at the 1, that is going to be significant. These zeros here will be counted because they're trapped. So this is 1, 2, 3, 4. More trap zeros here, 5, 6, 7. And now we have zeros at the end. And again, what determines whether or not this is significant is there a decimal point in the number? And there is right there. And that makes all 3 of these guys significant as well. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like most of you did good there. Very good. 10 of them would be the significant figures here. This just also illustrates the point that even though the zeros are way down here, the decimal is way over here. The decimal does not need to be anywhere near the zeros. Again, it just needs to be present in that number here. So if you had that's 625.00, I think is what you wrote, 625.000. This would be 1 significant figure, 2 significant figures, 3 significant figures, and again here the 3 at the end would be significant because there is a decimal point here. So 4, 5, and 6 would be here. Would be your significant figures. Yeah, so if we took the kind of like the example we had at the bottom here, 100 with the decimal here, this would now, because there's a decimal, even though there's nothing behind the decimal here, although I just kind of made it look like a 0, although there's nothing behind that decimal, these 2 zeros would then become significant, and this guy would have 3 significant figures in this particular case. And those zeros would be significant. They're trailing the last non-zero, so that's sort of what it means, sort of trailing that last non-zero. Now, when we talk about this, this is also a good example of what we were talking about in terms of the estimated digit. So let's take those 2 examples that we saw here, the 100 written with the decimal point and the 100 written without the decimal point here. Now, when we look at this guy, because this has 3 significant figures, that means that the last 0 here is our estimated digit or our uncertain digit, as the 1 and the 0, the first 1 and 0 would be the certain numbers plus that first uncertain number. So the estimation here is that the uncertainty is in that last 0, which again means it could be something like 101, could be something like 99 in terms of, the uncertainty of where that number may fall. But again, if we have this number here, as we just saw, it has one significant figure. And that would imply that the uncertain number and actually the certain number would actually be here at the first digit would be our estimated number. So again, not always the last digit because these zeros are not significant. So again, people would be tempted sometimes to go with the last zero. But because this has only one significant figure, both the certain and uncertain number is really this first one, which means there's a much worse of a measurement if you think about it. It could technically be 0 or like 200 in terms of the variation, in terms of where that actual number may be. So if you're sort of comparing two measurements that you're making, the one on the left there with the 3 significant figures, a much better measurement because again, the uncertainty lies in that ones place. Here, the uncertainty lies in the hundreds place, which gives you a much bigger area of error that could occur. Any questions on how to count significant figures there? Okay. All right. So let's also talk a little bit about rounding. When we do round, we sort of follow normal rules. What we're looking for is, again, anything that's less than 5. We essentially will drop off the numbers and just kind of leave the number where it's at. So if we wanted to go to 3 significant figures, I'll let you do it once you figure out what that would be based off of that number. So if your calculator gave you that, what should it be if you got to 3 significant figures in this case? Looks good. Yep. Yeah, that's looking good. So again, if we're going to 3 significant figures, starting over here, this would be our first non-zero, which would be 1, 2, and 3. Here we then would look at the 4, and we see it's less than 5, so we would round it to 3.72, which would give us 3 significant figures in this particular case. Coming down here, if we're 5 or more, we do typically round up. So again, why don't you guys give it a shot here, what you think you would get when you round that one to 3 significant figures, what the correct answer should be. Looking good, looking good. Yep, 5.01 looking good. So again, we get to 5.01 as we go from 1, 2, and 3. We are now going to look at this number here, which is above 5. So we're going to round up. And when we round up, we will end up at 5.01. So it's really important to try to round to the correct number of significant figures. You should always give your answer to the correct number of significant figures. And we're going to talk about calculations here in just a second in terms of, what to do when you do calculations. But it's really important, and where a lot of people sort of go a little bit crazy with the rounding and they end up with the wrong number. So for example, let's say we had 13,333. What would be the correct answer if you round to 2 significant figures? So take a moment, think about what it might be. What the correct answer should be if you round it to 2 significant figures. Okay. So looking like we're getting some answers coming in there. So when we look at some of the answers that I saw fly by, I saw 13. I also saw 13,000 fly by. All right, so let's talk about these numbers here. And these are, 2 numbers that probably would come up when people think about it. So if we're going to 2 significant figures here, we're looking for, starting at the left here, that 2 numbers would come to here. So here we're looking at this guy, and we would not round up in this case, right? Because it's less than 5. So we could drop the last numbers. So let's just first look at the 2 answers, the main answers that I saw fly by. 13 definitely has 2 significant figures. 13,000, written like this with no decimal point, also has two significant figures. So they are both correct in the sense of significant figures, but only one of them is really correct. And the one that is really correct, let me just give you sort of an example, and perhaps you could figure out which one is actually correct here. Let's say I owed you $13,333, and I say, I'm going to pay you two significant figures. Here's $13. My guess is I'm probably not going to make it out of the room there, right? There's a very, very big difference between 13, the actual meaning of the number 13, and the meaning of the number $13,333 versus $13. So although this number here at 13 is two significant figures, it definitely does not mean the same thing as our original number here. Now, if I owed you $13,333 and I say, hey, here's $13,000, well, perhaps you're okay with that because, you know, give me a $333 discount for being a good guy and all that good stuff. Good chance I could get out of the room as well. But, you know, the meaning of 13,000 and the meaning of our original number is approximately the same. And you want to be very, very careful, especially in a class like this where we do focus a lot on, obviously, giving the answers in the correct number of significant figures. You do want to make sure that you don't change the meaning of the number ever when you round. You always want to make sure that you maintain what that number means and don't actually change the meaning of it by just trying to get to the right number of significant figures. So that's a very important thing to keep in mind. You never want to change the meaning of a number by rounding. So this 13,000 would be the correct answer here, written like that. Just like we've been talking about, you would not want to write 13,000 with a decimal because now it has 5 significant figures in this particular case, nor do you want to move the decimal over here and write 13,000. Not 13.000, also has 5 significant figures, but also has now changed the meaning of the number as well. Still 13, right, ultimately. Another way you could do this, as we will see in a second, is you could write scientific notation 1.3 times 10 to the fourth, and we'll talk about it in just a second. But whenever you write anything in scientific notation, all those numbers before the times 10 part are always significant. So this would have 2 significant figures as well. So you want to do normal rounding, and really where people sometimes do get into trouble is, again, in that effort to get the right sig figs, they do some extreme rounding and they end up changing the meaning of the number, and you never ever want to do that. All right, so let's talk really about significant figures here in calculations. And there's really kind of 2 groups of calculations that you commonly do. You either multiply and divide, or you add and subtract. When we multiply and divide, which is sort of the top here, when you give your answer should have the same number of significant figures as the answer with the least number of significant figures. So multiplying and dividing, you're looking at significant figures, and you're looking for the least number of significant figures. So in this case, if we throw this into our calculator and we take 6.038 times 2.57, we're multiplying. This number here has 4 significant figures. This number here has 3 significant figures. So when we put into our calculator, one thing you probably are aware of, but just in case you're not, your calculator doesn't always give you the right number of significant figures. It spits out this number. And because we're multiplying 4 significant figures by 3 significant figures, our answer should have 3 significant figures, which brings us to this 5 in this number. And we should round this to 15.5 would be the correct answer here. So multiplying and dividing, least number of significant figures in your calculation is how many significant figures your answer should have. The other sort of situation that we come across in terms of math is we add and subtract. When we add and subtract, what we're looking for is actually decimal places, not significant figures. So we're looking for decimal places. And here we're also looking for the least number of decimal places. So when we're adding these numbers here, this guy has 3 decimal places. This guy here has 1 decimal place. And this guy here also has 3 decimal places, which means we should end up with an answer with 1 decimal place. And I'm going to grab the calculator. It's late. 9.33 plus 1.4 plus 10.733. And again, on your calculator, it spits out something like 21.466. Again, because this is the smallest number of decimal places, we should come to here, which means we do have to look at the 6, and we do want to round up in this case, giving us 21.5 as our answer. Now, 21.5 as our answer has 1 decimal place, but it has 3 significant figures. So you want to keep that in mind. It has 1 decimal place, but it actually does have 3 significant figures, but we go to 1 decimal place. The idea behind this is pretty simple. It's always the least. So multiplying and dividing, least number of significant figures, adding and subtracting least number of decimal places. And the idea behind it is the one with the least number of sig figs or the least number of decimal places essentially is your worst measurement. So your answer is only as good as kind of like your worst measurement, like that old saying, right? You're only as strong as your weakest link, right? And so your worst measurement is your weakest link in that measurement, and that what basically determines how your answer should be given in terms of significant figures. Any questions on that? Now, and again, if you have questions, feel free to ask them. Remember that we do oftentimes do multiple steps in terms of calculation. So sometimes you may be combining a lot of steps in terms of maybe you're multiplying, then dividing, maybe you're adding and then multiplying, so you just want to do it in normal sort of math order. So again, if we had something like we were taking 2.54 times 1.3 and then dividing that by 6.632, we would typically, in terms of math, do the stuff in the parentheses first. So in the parentheses first, we're multiplying, which means we are looking at significant figures. So here, this guy has 3 significant figures. This guy has 2 significant figures, which means when you get that answer up on top, technically you should end up with 2 significant figures. And then the next thing you would do is take that answer on top and divide it by the bottom number, which has 4 significant figures, which means when you're said and done, your answer should end up with 2 significant figures by doing that. So you do want to kind of keep track of what you're doing. You want to kind of keep track of the significant figures or what you should be doing in terms of measuring significant figures, and then really round things to the right number at the end of the calculation. So here, for example, if I did the top, I would take our 2.54 times it by 1.3, and that would give me up on top there, I'm just going to write it right here, up on top we would end up with 3.302, and then we would divide it by 6.632. And divided by 6.632 gives us 0.49788. I'll just go down underneath it, 9. And in this particular case, we would want to go to 2 significant figures, which would put us here, and that's a 9. And we would look at the next number, which is a 7, which means we should round up, and you should get something like 0.50. Which would be 2 significant figures in this particular case. Now, a couple of things on this. Typically, if you're doing a number of calculations in a row, it's not a great idea to round to the very end. If you're really strict about significant figures, in terms of multiple steps that you do in terms of calculations. If you round a little bit here, then take that number and do another calculation around a little bit there, and then take the number, do another one, round a little bit. Every time you do that little bit of rounding, you're probably moving your answer further and further away from the correct answer. So it's a good idea just to sort of keep track of the significant figures and clean it up at the end of your calculation. So, you know, although I didn't round here and I didn't on my calculator either, I should just, you know, sometimes people will put a line and go, okay, I should be about there in terms of the significant figures, and then kind of come back through and clean it up at the very end, which is kind of like what I did there in that calculation. Any questions on calculations that involved significant figures? Yeah, so the question is the adding example over here, the original example, where we got to here. When we added it together, you got 21.466. And because when we looked at all these numbers, we're not looking at significant figures, but we're looking at decimal places for the answer. So the answer should have one decimal place, which means we should round to here, which is what we did. We rounded to the 5, and we did need to round up because of the 6. Now, this number has one decimal place, but if you were asked how many significant figures this number has, it has 3 significant figures, as starting to count with the 2, which is significant, the 1 is significant, and the 5 is also significant as well. And that's how you would get 3 significant figures in that particular case. And again, the distinction there is when you're doing sort of the rules for adding and subtracting, it is decimal places. And sometimes people get that decimal places in their head and forget that that number has more significant figures. And that would be important. So for example, let's say we did this calculation, you know, in this process here, where we had the 9.33 plus the 1.4 plus the 10.733, and then we're going to multiply it by 1.356. So if we did all this, which is pretty much the example we started with, we would end up with this number, which is technically 21.5. And technically speaking, it has now 3 significant figures. And that's important because then we would technically take the 21.5 and multiply it by 1.356, which was, we're looking at significant figures here. And that would tell us that our answer should end up with 3 significant figures in that particular case. So it's important to recognize how many significant figures a number has, especially if you're going to take that number and perhaps continue on within the calculation. But again, 2 distinct things you're doing: multiplying and dividing, you are looking at significant figures, the least. And when you add and subtract, you're looking at decimal places and also the least. Other questions on that? Okay. So let's talk a little bit about scientific notation. And again, a lot of times in science, especially chemistry, we have a lot of numbers that have a lot of zeros involved. And sometimes these zeros can be lost if you try to write them out, and you may lose them, especially if you're starting to do some calculations. So we oftentimes will use scientific notation to handle really large numbers or really small numbers, like the ones you see on the screen. Clearly, if you're going to write those to do some calculations, I would bet you would lose some along the way, you know, as you're doing it. So we use scientific notation to help us sort of handle these larger numbers. And scientific notation has this general format here of n times 10 to the n. The n is a number between 1 and 10, so not 10 or anything like that, a number between 1 and 10, times 10 to the little n. And again, the little n is either positive or negative, and it's basically how many places you moved it either to the left or to the right to get to a number between 1 and 10 in that particular case. So let's see here. Let's take a look at some examples here. These are not negative, that's just PowerPoint, so we'll just look at these numbers here. So 568.762. Here we would need to move the decimal place 1 and 2 places to the left to get to a number between 1 and 10. So that would give us 5.68762 times 10 to the 2. I move the decimal place to the left, it's a positive exponent. If I move the decimal place to the right, it will become a negative exponent. So why don't you try the rest here and see what you come up with in terms of scientific notation. And we'll talk about it here in just a second. So give it a go. And again, none of these are negative, so I'll just scratch them out. This is from PowerPoint. So turn each of these numbers into proper scientific notation and see what you come up with. Take a minute or so to do so. All right, so let's take a look here. So here, our decimal is here. We need to actually go to the right. 1, 2, 3, 4, 5, and 6 places to the right gets us 7.72 times 10 to the minus 6. So we move the decimal place to the right. Our exponent is negative here, as opposed to here, we moved it to the left. Our exponent is positive here when we put in scientific notation. A good way to remember it is larger number, positive exponent, smaller number, negative exponent when you do that. In this particular case, there is no decimal point written. It is assumed to be here, even though it's not written. So we would go 1, 2, 3, 4 places to the left, 1.25 times 10 to the 4th. Here is a larger number, positive exponent. And again, you may ask, what happened to our zeros? And again, it has to do with what I talked about just a little bit earlier. It has to do with significant figures. When we look at a number like 12,500 written like that, it does not have a decimal point written, which means significant, 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 zeros at the end, not significant because there's no decimal point, which means this has 3 significant figures. By the way, the uncertain value or estimated value then would be the 5 in this case. What that means is when I write it here in scientific notation, if you remember what I said just a bit ago, whenever you write a number in scientific notation, all the numbers that come before the times 10 part are significant, which means that this number would also have 3 significant figures the way it is written. And you should never lose significant figures or gain significant figures if all you're doing is changing it into a scientific notation. This number here has 6 significant figures. This number here has 6 significant figures. This number here has only 3 significant figures, which is why this has 3 significant figures. And to answer your question, that technically would be incorrect if you wrote it 12.5 times 10 to the 3. And that is because it does have 3 significant figures, but proper scientific notation is this first number needs to be a number between 1 and 10. Not 10, but a number between 1 and 10. And 12.5 is not a number between 1 and 10. So technically speaking, this would be incorrect because of that fact. So proper scientific notation is always a number between 1 and 10 times 10 to the whatever it may be, which is, again, why we have this here. So you always want to remember that, and that's a common thing that people will sometimes do as well. So that first number, always a number between 1 and 10 in that case. Now, if we get here to the last one, we do need to go one place to the right to get to a number between 1 and 10, and that would be 1.35 times 10 to the minus 1 in that particular case. So really important to know how to write significant figures and make it into decimal form and out of decimal form. Same thing here. We have 3 significant figures here. Again, all the numbers before the times 10 part is 3, and we maintain it. Any questions on that there? So let's talk about, obviously, really important in terms of scientific notation, and a couple of things about scientific notation. You don't necessarily have to give an answer in scientific notation unless it specifically asks you to do so. The only thing that you do have to do is give it to the right number of sig figs or whatever that may be. Now, there may be only one way to get a number into the correct number of significant figures is to write it in scientific notation, again, because you can basically control the significant figures. So, for example, let's say we had this number here, and we wanted to write it with 2 significant figures. Let's do it. Let's do, I don't know, let's do, yeah, well, if we want to write that into 2 significant figures, we could do it by doing 1.3 times 10 to the 4th. And again, now we're able to control that to 2 significant figures. If we want to write this to 1 significant figure, we could do 1 times 10 to the 4th as well. So with scientific notation, you can sort of control how many significant figures your answer gets, which makes it really good in terms of getting a number into the right number of sig figs. And again, sometimes there may be only one way to sort of do that when you want to write an answer in scientific notation. So for example, again, get rid of some of this. Say we had actually 12,000, I think is what I'm trying to think about, and we want 3 significant figures. So if we want to write 12,000 with 3 significant figures, there's really no way to do it correctly in decimal form. You put a decimal at the end, you have 5. You put a decimal after the 2, you have 5. You know, if you cut it out to 120 with a decimal, you change the meaning of the number. So again, the only way you could kind of maintain the number and keep the 3 sig figs, 1, 2, 3, and 4, is to write it in scientific notation like this, where the 1.20 would be your 3 significant figures. Now, when we do calculations, it's really important to know how to type it into your calculator. So again, on your calculator, you have an EE button. It's actually your exponent button, an EXP button, and some of you may have a times 10 to the n button. And if you have these 2 buttons, these are pretty good. If you have this one, it's okay, except you do need to put parentheses around every single number you put in there. Otherwise, you will get the wrong answer. If you have an EE button or an EXP button, you don't need to put parentheses. You should be fine just the way it is. So let's erase some of this stuff here. So I got somewhere to sort of write a little bit. So let's say we did want to put some numbers in our calculator in scientific notation. So let's say we want to do this number here. If we were going to type this number there, you would hit 1.3. You would hit your exponent button, so your EE button, your EXP button, and then most likely on your calculator it will pop a 1.3 and an E, or it may do a 1.3, maybe pop up some zeros or something like that. And that E or the 00 are when you hit the exponent button. These guys stand for the times 10 part of the number. And what that means is you should not hit the multiplication button. You don't have to do inverse log or shift log or anything like that. You just need to put in what's left in terms of the number, which is a 4. You would hit 4. It would pop a 4 here. It would change this guy into a 4. And this would be proper scientific notation the way you push it in. Again, no multiplication button, no inverse log, shift log, or anything like that. That is the proper way to do that. If you have this button on your calculator, which some of the newer ones do, you have to do the same thing. The only difference is you need to kind of put parentheses around it. You can go 1.3, you got to hit that button, and you hit 4, and make sure you put parentheses around the whole number. There's also a negative, non-negative number, a negative button actually. Looks like this, positive, negative, or on some calculators, this button. So if you have a negative exponent, you would punch it in the exact same way, except you would hit your negative button, not your subtract button. Otherwise, you will get an error. So you want to make sure that you, more importantly, know how to punch these into your calculator in scientific notation correctly. The way you can usually figure it out if you're doing some calculations, you're trying to punch things in scientific notation, and you get an answer, say like this answer, and you'll go, all right, this part looks good, but this number here on the exponent part is a little bit off. And that's usually because of the way you entered it into your calculator. You're not using the proper buttons. So let's just try a couple here just to make sure. Take 3.25 times 10 to the minus 3. And let us divide it by 1.11 times 10 to the 14 and see what you get. And let's do 3.33 times 10 to the 16, multiply it by 1.4 times 10 to the minus 6 and see what you come up with. I'll do it as well and see if we end up with this right answers. So take a second and see what you get. Also try to put it with the proper number of sig figs on your answer there. Make sure you get it all correct. Just clear up some space while you do that. Okay, let's take a look at number 1 there. And again, if you were going to punch this into your calculator, what you want to do is go 3.2. Again, hit your exponent button. No multiplication button or anything here. That stands for the times 10 part. You then want to hit your negative button and 3, and that would represent the first number here. You obviously then would want to hit your divide button, and then 1.11, again, exponent button. And in this case, it's a positive exponent, so 14, and hit equals. Yeah. And if you do all that, you will end up with a number that is 2.8 9 times 10 to the minus 17. Now, a couple of things just in case, hopefully you got the right answer. By the way, on your calculator, it will say, it will say 2.88288 times 10 to the minus 17. I rounded because I'm multiplying. This has 2 significant figures. This guy has 3 significant figures, and that means that my answer should end up with 2 significant figures. Now, if you got the front number here and it's correct, and the back number is not right, like this number, it probably is the way that you're putting it in your calculator with your exponent button. If you got something completely off of this, it's just maybe the way you're putting it in. But again, don't use the multiplication button or anything like that. The other thing that's very common is people will sometimes forget when they look at their calculator, you know, they'll have this number 2.88, 2.88, you know, 288. And then on some people's calculator, again, it may put it like way up on top or something like that. And they forget the exponent part, which is this part of the number. So again, sometimes people will oftentimes forget that part, and you don't want to do that. Let's take a look at number 2 here. Again, putting it in 3.33 exponent button. And our 16 in this case, as it's a positive exponent, we would then hit our multiplication button, 1.4 exponent button, and negative button because it's a negative exponent, and 6, and hit equals. For the first one, if you're talking about this one was a positive 14, if that's what you're talking about in terms of that one. The first one was a positive 14. The answer was a negative 17 on the exponent, but the actual original question was a positive 14 here. And if you do that for the second one, 3.33 exponent button, 16 times 1. Get the right number, 1.4 exponent button, negative button, and 6 for our second one gets us 4.7 times 10 to the 10. Again, for significant figures, 3 sig figs here multiplied by 2 sig figs gives us 2 significant figures for the answer. Questions on exponents. Really important to understand how to properly punch these in. And again, if you're finding yourself like it looks very close, but it's just that exponent part that's off, it is probably how you're punching it in. And again, if you have this button as your exponent button, you definitely need to put, in my experience with those calculators over the years, just the way they're programmed, you pretty much need to put parentheses around every single number. So, you know, you would use obviously your exponent button, but you would have to throw parentheses around both of those numbers as you punch them in using that exponent button. Any questions on how to punch it into your calculator, your exponent button? Usually I would tell you, bring your calculator and show me, we'll find it together. But again, during discussion as well, if you need some help with that, we could probably figure it out, you know, on your calculator, how to punch it in if you need that. Yeah, we could do one more example. Let me just find somewhere I could scribble one. Let's scribble one here. So if you did, let's do a bunch. Let's do a couple of things together. Why don't we do 3.2 times 10 to the minus 2 plus 1.2 times 10 to the minus 1. And let's divide it by 3.25 times 10 to the 6 and see what you come up with. And also try to get the right sig figs when you're all said and done. Okay, so let us take a look. I see some answers rolling in. All right. So we're going to do the part in parentheses first. So we're going to do 3 point, maybe hit the right button here, 3.2, exponent button, negative button, and 2, plus 1.2, exponent button, negative 1. I personally would hit equals at this point. And if you do that, you got something like 1.52 times 10 to the minus 1, or 0.152 if you're not in scientific notation. We're then going to divide it by 3.25 exponent button 6 and hit equals. And this is the number I get spit out on my calculator, which is in scientific notation, 4.6769230077 times 10 to the minus 8. If not, you have a bunch of zeros. 1, 2, 3, 4, 5, 6, 7, and maybe something looks like this, I think. One. Like on your calculator, probably, if you're not in scientific notation. So this is sort of the right answer, not the right answer yet in terms of perhaps what we should end up with. Let's take a look at what we were talking about here. We're first adding, and if you did just convert these numbers by themselves, this would be 0.032 plus 0.12 in the parentheses if you just took it out of scientific notation. Since we're adding here, we would go to decimal places, which technically means we would have up on top there this answer, which was 0.152. Technically speaking, we should go to 2 decimal places, which brings us to here. So really this number on top should be 0.15 divided by our bottom number, which is now 2 significant figures up on top, 3 on the bottom, which means our answer should end up with 2 significant figures, brings us to here, and we should end up with 4.7 times 10 to the minus 8, which looks like a lot of the answers in there, which is really good. And any questions on that? The calculations, the scientific notation, really, really important to know how to punch these things in correctly. There's going to be a lot of numbers throughout the semester that will be in scientific notation. Half of the battle for most people, is the calculator, and not being able to sort of punch it in correctly. Any questions on that there? Okay. Let us continue on then. So we're going to talk about conversion factors and writing conversion factors. And conversion factors are really just fractions. So there's a denominator and a numerator, and they're basically made from an equality. So from any equality, for example, like if you had 100 pennies equals $1, that is what is known as an equality. They're basically 2 different units, but they represent the same amount of something. So they're both basically money. They both represent the same amount of money. You could go through the drive-through and pay in pennies. You could go through the drive-through and pay in dollars. Although if you do pay in pennies, they may put a sign up there and not let you through the drive-through, but they do represent the same thing, technically speaking. And from any equality like that, you could write 2 conversion factors, which is 100 pennies, in this example, over $1. Or you could say $1 is 100 pennies. Will you use these conversion factors? Both of them. You will not in a problem. You'll just use one. And basically what we're going to be using it is in what's known as dimensional analysis. And we use it to get rid of units and show the units. So for example, if I started with 700 pennies, and I want to know how many dollars that would be, I would start with my 700 pennies. And although this is not really written as a fraction, it is like a fraction, like this is over 1. And what that's important is the pennies in terms of those units are up on top. And when we do conversion problems, to get rid of units, they need to go in the opposite location. So on the bottom would go 100 pennies, so they cancel. Up on top would go $1. And the units of pennies would cancel each other out, because essentially what we're doing is we're taking pennies and dividing it by pennies. So it equals 1. Same thing if you took 2 divided by 2, it equals 1. Same idea. 1 unit on top, 1 unit on the bottom, that's the same. They basically cancel each other out and become 1. Math-wise, what we would do is take 700 times 1 and then divide it by 100. And we can go without a calculator on this and go with $7 in this case would be our answer in terms of that. So this is what's known as dimensional analysis, and what we try to do is use conversion factors to go from one unit to the next, but you do need to show the work with the units canceling and sort of set up like I just did there using the conversion factor. Now we could get conversion factors from many different places. For example, if we say we're driving 65 mph, mph is miles per hour, which means essentially what that means is you could go 65 miles in 1 hour. And from that, you could write 2 conversion factors. One would be that there are 65 miles over an hour, or in an hour, there is 65 miles. And this would be 1 hour in both cases. And again, you could use this to know, for example, how long it would take you to drive somewhere. So if you drove 65 miles per hour, how long would it take you to go, 265 miles? So again, sort of setting it up in this dimensional analysis way we're going to talk about. You say 265 miles. Again, not really a fraction, but the unit of miles are on top, which means to get rid of the miles, we need it on the bottom. So we would want to use this conversion factor. And we would go 1 hour. We could go 65 miles. Again, we're going to cancel out the units of miles because miles on top, miles on the bottom will cancel. We would take 265 times 1 and hit equals, and then divide it by 65, and that would give you your answer. And in this particular case, it looks like it would be 4.08 hours, as that's the only unit left in my little example there to go 265 miles. Now, here's a bunch of equalities. Some are metric and metric, some are English to metric sort of relationships. Some of these, you should be familiar with. We do use them a lot along the way. 12 inches is a foot, obviously. Where are we at here? 1 inch is 2.54 centimeters. I'll get to your question about significant figures and conversion factors in 1 second. It's actually a very good question, and we're going to get to it, I think. Maybe the next slide, hopefully, I think. We also, 5,280 feet in miles, one we use a lot. A pound is 454 grams. So these are ones we use a lot. So for any of these sort of conversions here, you could write 2 conversion factors. And for example, you could say there's 454 grams in a pound, or 1 pound is 454 grams. Now, when we talk about sort of conversion factors, they are considered what is known as exact numbers. And exact numbers are things that are either counted. So for example, if you had 5 apples on your desk, you wouldn't do any type of weird scientific process to figure out how many apples you have. You would simply just go to your desk and go, I got 1, 2, 3, 4, and 5 apples. Are there definitions like 1 inch? Like we see here on this table, 1 inch is 2.54 centimeters. There's 454 grams in a pound. So any type of equality is considered an exact number, and they do not have I don't say that right. They're considered an exact number, and really what that means is they have unlimited amount of significant figures. And what that means is when we do a calculation that involves a conversion factor from equality, like we did here in this example, or even we did here in the previous one, we don't count the significant figures in this number. So this was our conversion factor for my first example. My original number here, the way I wrote it was 700 with no decimal point, has one significant figure, which means when I got my answer, I should have one significant figure. Again, ignoring the conversion factor here, as is considered an exact number. Same thing with this one that we did. My original number here was 265 miles, and I went 65 miles per hour. In this particular case, you could have went 4.08 hours like I did based off of this, but probably because this is not a legitimate conversion, probably 4.1 hours would have been a better answer, because I didn't put the 0.0, which I meant to do here. So since this is not really a legitimate sort of conversion, like 1 inch is 2.54 centimeters, we probably would look at the 65 and use the two significant figures as the proper numbers for our answer. But in most cases, probably 9 times out of 10, if you have any type of equality like you have over here, you probably can consider an exact number. You don't have to worry about it in terms of the calculation. And you can basically just start with the original number. So most cases, if you use the original number in a conversion and all you're doing is a conversion factor, you typically will have the right number of significant figures in that particular case. And that's usually the case, what will happen. So any of these here, don't have to worry about sig figs. Again, 9 times out of 10, if you default back to the original number in the calculation, you'll probably have the right answer in terms of sig figs. So I think that answered your question. There are some that you should know on the review sheet. It will tell you exactly which ones will not be provided for you. So if you look at this, for example, the exam 1 review sheet, it will say, for example, I know you should know 1 inch is 2.54 centimeters. So that will not be provided for you. So again, that's something that you do need to know sort of by heart. So it'll tell you specifically which ones to know, which means it probably won't be provided. So you should know those guys. Okay, so I think I got all the questions there. When we do dimensional analysis, which is sometimes called problem solving, these are several steps that we could use to solve a problem. For example, we could write what's given in the problem, think about what we're trying to find, write the appropriate equalities, the conversion factors, set up the problem so that the units cancel correctly. That's the dimensional analysis part. And that's hard for some people, but that is what the work you need to show is those units canceling and set up. And you should solve the problem, obviously, if you have some time. So why don't you try one here? Let me give you some equalities that may help. So take a moment or two here. And what we're looking for is we went to the AMPM, got 32 fluid ounce drink. How many gallons of Diet Coke did you drink? So take a couple of minutes here and see what you come up with, and then we'll talk about it. Okay, so let's take a look here. So again, we want to start with what was given to us, which was 32 fluid ounces. So we want to go from fluid ounces perhaps to quarts, since we have an equality. Remember, from this equality, you can write two conversion factors. So again, opposites is what cancels. So since fluid ounces is on top, I do want the 32 fluid ounces on the bottom. And up on top, we would go 1 quart. At this point, if we stop, the units of fluid ounces would cancel each other out. We would be at quarts at this point, which is close to what we want, but we do want gallons. So we are going to use our other equality here, which we also could write, again, two conversion factors for, which looks like this. Again, you could get an answer, or you could continue on with the calculation. I'm going to continue on with the calculation. Quarts again are on top, but we want to get rid of it. So we want to go opposite. So we will use the one where quarts are on the bottom so that they cancel. Quarts cancel here, leaves us with just gallons. In terms of the math, we're going to take 32 times 1 times 1. I would hit equals at that point. Then we will divide it by 32. I would also hit equals after that, and divide it by 4 and hit equals after that as well. And if you do that, you will end up with 0.25 gallons. Okay. This is a conversion factor, exact number, don't have to worry about sig figs. This is a conversion factor, an exact number, don't have to worry about sig figs, which means the only sig figs we got going on is our original number, which was 32 and 2 significant figures, which means we should end up with 2 significant figures here. Also, the right answer is not 1 divided by 4, because that makes me think you're too lazy to divide. Because I've had very bad instances where people will give an answer like 425 miles over 632 hours, and that looks good enough. Yeah. Again, divide it out and get an actual number. And here in this class and most classes that you take, don't really leave answers in terms of fractions or anything like that. Make sure that you do that. So again, any type of conversion factor is essentially an exact number. You don't have to worry about it in the calculation part. I will say for our class, and keep it simple, any type of equality will be considered an exact number. There are people that say if you go between metric and US, you should look at sig figs, but we're not going to worry about that. But just to let you know, sometimes people do that. So anything in our class that's an equality, you could consider an exact number, which again means probably 9 times out of 10, whatever significant figures that first number has, and all you did was conversions, you should be good. That's how many significant figures your answer should have. Again, not 100% of the time, but in most cases. Any questions on this particular one here? All right, give the next one a try. Give you some equalities that might be helpful. There you go. How many milliliters of plasma were given in this case? Looking good. Looks like we're getting some numbers coming in. All right, let's see if I agree or disagree. Let's see. So we got 5 pints. So again, here we could go from pints to quarts and quarts to milliliters, which is what we're looking for. Again, you do need to show this dimensional analysis approach. So pints are on top, so we could use our first equality here. We want to put the pints on the bottom. Again, opposites cancel out. So 2 pints and 1 quart. Again, the pints are going to cancel. We will be left at quarts at this point, which again, you could get an answer or you could continue on with the calculation, which is what I'm going to do. Quarts are on top, so to get rid of it, we want the quarts on the bottom. So 1 quart will be 946 milliliters. Again, the quarts will cancel. That's going to leave us as milliliters as our only unit, which is good because that's what we're looking for. We're going to take 5 times 1 times 946, hit equals, divided by 2, hit equals, gives us an answer on the calculator of 2365 milliliters. Now, in terms of sig figs, this is an exact number, so we're not going to worry about it. This is an exact number. We're not going to worry about it. 5.0 has 2 sig figs, which means technically this guy should end up at 2 significant figures, which means the correct answer should be 2,400 milliliters, no decimal written, which would be 2 significant figures, or 2.4 times 10 to the 1, 2, and 3 places milliliters, which would also be 2 significant figures. So remember, it looks like most of you got the right answer in terms of punching it in, which is really good. But again, you've got to make sure at the end that you do clean it up to the right number of sig figs. And again, in most cases, if it's just a conversion, probably the same number of significant figures as that original number. Questions on that calculation there? Okay. Now we got one more here, I think. So see what you come up with here. You're 125 miles away from home and you decide, hey, let's walk. Nice walk. If you're going 55 feet per minute, how many days would it take you to get home? There's 5,280 feet and 1 mile might be helpful, I think. Are you asking about what about the 2 for 2 pints? Are you asking in terms of sig figs? Yeah, so this is still an equality. This is an equality. We divided by 2. Is that what we're asking? So on this one, we took 5 times 946, hit equals, divided by 2, and then that's the number that we got. This whole thing is in a conversion factor or equivalent, so you don't have to worry about it in terms of sig figs, and same thing with this guy, so the 5.0. The pints canceled out originally because we started with pints, so the pints and the pints canceled out. All right, so take a minute or so here, a couple here, and see what you come up with. Okay, I'll tell you what, since we're getting kind of to the end here, why don't you finish this one up and we will start with this next time on Wednesday. And we will start with this one on Wednesday and we will finish it then. a couple of things here before we sign off for lecture. A reminder that if you have discussion tonight with me, make sure you come back through the discussion link. Obviously, if you have lab, you should be going to lab today as well. And make sure that if you didn't type here into the chat box that you do for roll. And other than that, take care of the business privately. Yes. We will wrap it up here, I think, for today, so you can get over to lab, because there's not a big break between. All right. If there's no other questions, make sure you type here, and I'll see everybody in discussion in about 5 minutes. And again, those that have lab, head on over that way.